There we go. Do you want help pulling it? You think you got it?
I think I got it.
All right. 3, 2, 1, pull. 3, 2, 1, pull. That's probably some of the best launches today. What's up, guys? Welcome to our first big build we have for this channel. As you've been paying attention at all, we have a really fun event coming up called STEM Day here in about 2 weeks. And I wanted to start building stuff in the size of ridiculous. It's something that, a student could come in and be like, well, I just did this with my dad on the weekend, or something they've already done. I wanted to get so large that we start getting in the realm of sketchy, and that's what this trebuchet was, is how big can I make a trebuchet and it work? I've never built one before. I did tons of research kind of leading into it, and we have a successful product. So let's unpack kind of our constraints, look at the CAD model, and then kind of watch some clips here soon of me walking through what some changes look like before we had actually a working prototype. So the first thing is that, one, we had some limited funds for this, not too constrained, but definitely the more we got our money to stretch, the better. Two, I wanted to get everything I needed to get at a hardware store. I wanted to not special order any pieces or need any specialty tools for building this. So you see these axles here. I knew I was going to use steel pipes with some T's on the end that students can hand tighten, or at least maybe use some pliers to tighten and loosen. That way we actually don't need any power tools. So we needed cost efficient. We get everything in a hardware store, and then also it needs to be able to be taken apart and put together without any power tools and fit through a regular sized door. We need to be able to bring it inside. There's no way I'm going to let this thing just chill outside for an entire year before we use it again. So how do we do that? In the video, I kind of unpack some of those things. If you have some questions, feel free to throw it down in the comment section. But I am going to talk about why we did certain things. First thing is I was thinking about what my counterweight is going to be. This is kind of what the whole design process looked like. Where did I start off with? Well, I knew I had 45-pound plates in the weight room I could probably borrow. So I started with, what is the inside diameter of those plates? And that's where we started. We started off with 1.5 inch axle for the steel pipe. That then predicated what thickness I needed for my plank. If I did a 2x4, there was really not going to be very much material there. So instead of going with a 2x4, we went with a 2x6. That way there's enough material for that 1.5 inch to be cut through and to not cause the arm to snap because there isn't much material left. So we went with 1.5 inch pipe and a 2x6 for that reason. Almost the rest of this is also built with 2x6s. As I was building, kind of see on, there's some places where I was able to do stress tests on OnShape, but as I was building it, I thought, oh, easily we can reinforce it. So one way I had to reinforce it was a second set of truss beams that run down this center beam right here, and then also ones that run outwards and at kind of an L shape, and you'll see that kind of later in the video. One thing also not really shown in here is that this is able to separate. I show that in the video. Like I said, if you got any questions, feel free to throw them down in the comment section. I'd love to help you out. This I'm going to call a smashing success. Definitely pun intended. And hopefully you can watch the rest of this video and see some good stuff for yourself. Take care. All right, guys, we have the trebuchet built in the classroom. Let's unpack some things that might be helpful for you if you want to build one of your own. First thing being is that I built this out of 2x6 planks rather than 2x4s. I found it to reinforcing it, especially some of the axle diameters we needed for our 45-pound plates. I got really unsure that the woods were going to split with the grain. So now I'm going to talk about why you need 2x6s, but also how we're going to reinforce them so they don't split. So let's go through our list of materials we're going to need to make this work. We have 6 45-pound plates. I thought I was going to use those 25-pound plates, but we didn't need them. We have 3 medicine balls. One is 4 kilograms, so it's 8.8 pounds. Then we have a 6 pound and then a 4 pound ball. We have a 2 pound ball on the way. I'm going to test to see if those launch well, but I'm not actually sure it's going to create a better result, just because that 2 pound ball is going to be a little more applicable or resistant to wind friction, and so I'm not even sure that that 2 pound ball is going to have enough momentum to continue carrying forward. I think air drag is going to play a huge role in that. One thing you're going to know difference in the solid model is because as I was building this thing had a really big tendency to wobble kind of left to right here, and so to help counteract that, we throw on some arms that go on the outsides at 45-degree miter with some plenty of structural wood to hold those up nice and sturdy. Since this is now preventing it from going left and right, I've got a whole lot less wobble, and it just really, really worked and came out nice. All right, let's look at how we got this trebuchet to fit through that door over there. The left and right sides of these trebuchet can disassemble, so the platform on the left side and the right side can detach. If we zoom in just a little bit closer, so there's 2 connection points. One on the left side, one on the right side, and then one down there. But this plank is held together on these two with just a thumb screw and a bolt, 3/8 inch bolt. It's a little bit overkill, but I think overall this allows the students to put this thing together and take it apart without needing any power tools whatsoever. Once the 2 planks going across are fastened in with the thumb screws and bolts, this platform just rests on top, like so. All right, now let's talk about hardware. So for most of this, we used 3-inch wood decking screws, which worked pretty well. However, in the areas of high reinforcement, we went ahead and used lag bolts that are 6 to 8 inches, depending upon how many boards we were trying to go through. So let's look at what we did to the arm to reinforce it. All right, the areas where we need lag bolts is if we had the amount of material going through is longer than 3 inches. So on this angle right here, since this is longer than 3 inches, we had to use a lag bolt that goes all the way through. Kind of same down here. On the arm, you'll notice we look downstream that this is 2 2x6s tacked together, and that's with some wood screws kind of every 16 inches or so, and we did that to both sides. Maybe a little bit of overkill, but I want to make sure that this thing doesn't fall apart. Now here's where I think my genius comes from, is to make sure this axle weight doesn't split. So right here, if I take a step back, this is where most of the stress in the system is going to be. If there is 270 pounds over there, and we also have the weight of this lever arm, that's going to be a lot of weight kind of resting on not a lot of material. So to help fasten it, we just drove a lag bolt all the way through 4 spots over here and on the underside, just to make sure that this 2x6 doesn't split this way with the grain. After a couple tests, things look really good. I don't see any signs of wear and tear, no cracking, and so I'm really, really happy with that progress. All right, now let's talk about axles. We chose an axle that was the same diameter. The outer diameter of the axle matches the inside diameter of the weight plate. That way it fits on really nice and snug. Remember, we didn't want to get any supplies that we couldn't find in a hardware store, so we chose some standard lengths. The first standard length was this 3-inch long pipe. It is plenty sturdy, plenty strong. The weight stress on it, not concerned one bit. But I didn't want to have to create any threads. I don't want to have to do any welding. All I wanted to do was to be able to throw on a cap at the end and call it done. So we chose a 36-inch pipe here, and then put on some rubber collars that you would usually find for PVC fittings to help prevent this arm from sliding back and forth. I did have a little bit of an issue there, so that's a new piece that wasn't on the solid model earlier. As far as to make this thing easily disassemblable, we have some of these T-nuts, which can be removed by hand. So when we crank these down, we're going to crank them down with a big wrench or a big pipe, and then really snug fit on them. But we're able to take this thing all the way apart without a single power tool, or at least that's the goal. As far as to make sure we had clearance, we chose the next smallest pipe size, which was 18 inches. Those 18 inches allow us to stack 3 45-pound plates on one side, 3 on the other. This one up on the top side, I probably could have gone with a smaller size, but I don't think they had them on stock. I think I just had to walk away with an 18-inch pipe and then just call it done. As far as to help to make sure that none of these weights cause the grain to split, we did the same thing we did earlier. We reinforce with plenty of screws down at the bottom, again, because this has got 270 pounds of material, and we don't want this weight to split. So what do? Is we have plenty of lag bolts going through kind of all directions. Might be a little bit overkill, but it worked nonetheless. Okay, for the release mechanism, we're probably going to create a small adjustment here when it comes to this. Since this release pin is only on one side, this arm wishes to pull towards us to the right rather than being a true center. So there's probably going to be a small adjustment made here. However, it still worked nonetheless. So when the system's under tension, we have the string, all of that force is held on just by that string. Give it a quick pull, string releases, arm goes flying forward. As how we got the sling to attach, one part of your trebuchet needs to be fixed, and the other part needs to be able to slide off at the top of the sling. Just using a rope cleat, and it worked beautifully. I thought I was gonna have to change the angle of this and try to bend it. Beautiful, not a problem. As far as the sling length, since my arm is 6 feet in length from the center of the axle all the way to the edge, I chose to do a 4 foot length on the rope, just so I didn't run into any issues on the release. How did we make that rope? Okay, let's follow this sling all the way through. So here's the hitch mount. This is permanently fixed to it. I probably need to clean up that knot a little bit, but this part of the sling is fixed. This cleat right here is where it slides off. So let's follow this rope all the way down about 4 feet. We meet the sling. The sling is an egg shape, or that football shape. More on that in a second. We continue all the way down about another 4 feet. We see the rope loops back and is one actual continuous rope. We like that because that means this sling can slide to the left or slide to the right based upon what it needs to do. How do we make it? Let's look at that a little bit more closely. Huge thank you to Mrs. Fulton for making our canvas sling. Here's how she made it. I got some heavy-duty canvas from the painter section. She was able to cut 4 layers thick and then fold it over and create a stitch right here. Since that stitch allows the rope to slide through on both sides, it allows 2 things. One, it allows the sling to move up and down the rope to find its best spot during launch, but also allows the sling to bunch up around the payload. So I'm gonna hit pause real quick right here and kind of show you what that looks like. All right, I don't know if the video does it justice, but we can see that the canvas is bunched up a little bit more. And if we fold this over, we can see the ball is held a little bit more on the inside, since that canvas does bunch up around the edges of the ball and it doesn't really fall out very easily. All right, there you have it, folks. We built the trebuchet. Now you're welcome to build one of your own. If this encourages you to build a trebuchet either at your school or in your backyard, please let me know. I would love to see that my contraption has convinced somebody else to make one at their school or even in their backyard if you're just that kind of cool. But in any case, you guys are awesome. Stay awesome, and I will see you guys in the next video. Take care. Your shoes look fantastic. I should wear some pink shoes. So let's go. Well, all right, so what's your name? What's your name? You gotta speak to the camera. What's your name?
Coco.
Coco? Hi, Coco. And what are we doing today?
Today at home, we're going to eat a snack
Yeah.
that's black.
You had a black snack? Was it Oreos? Was it cookies? Was it raisins? No? What was it?
I don't know. I forget.
Yeah?
It's gone.
Well, and what are we doing here? What are we doing here?
We're going to lift up a ball.
We're gonna lift up a ball? Okay, and what's your job?
My job is to lift up that.
Yeah? You're gonna pull on this string, right?
Yeah.
And we're gonna pull on the string and then it's gonna let go?
Yeah.
Okay. All right, you ready to do it? All right, let me put this camera down. What a line! That's pretty consistent too.
Yeah.
That should have been an engineer.